Zoom.
Okay, guys. So sorry for your long waiting, and thank you for your presence. The title of my presentation is a structured prediction approach to robot imitation learning. Before moving to the technical details, I will introduce myself a little bit. From October 2021, I will be a research associate with the romi-lab. And previously, I obtained my PhD in robotics from Italian Institute of Technology. And I got my Master of Science degree from KTH and a Bachelor of Engineering from Harbin Institute of Technology. Okay, first, the motivation for imitation learning. Why should we consider imitation learning? Well, from a psychological point of view, if a robot can behave in a human-like manner, then it is more acceptable for a human coworker to work besides a robot. And from a scientific point of view, for some tasks, it is quite difficult to design a reward manually. So we can consider to demonstrate the desired task first and let the robot imitate the desired behavior. And from an engineering point of view, some robots possess high degree of freedom. So it's very hard to command the trajectories manually. So in this case, imitation learning is also a good tool. Next, what to imitate? Besides trajectories, there are many quantities that can be imitated by a robot. For example, in a task such as cleaning a table, it is critical to make sure the palm of the robot is perfectly aligned with the surface of the table. So in this case, we need the robot to imitate orientation well. Also, in this pull and pushing task, manipulability matters. So manipulability could be the quantity to be imitated by the robot. And in this wood cutting task, stiffness plays an important role in realizing the task. Here's the roadmap of my presentation. First, I will introduce the probabilistic imitation learning framework from a multitask sequencing perspective. Then we move to the case where inherent constraints exist. In this part, we will see a structured prediction approach to robot imitation learning. And then when a policy is learned, we try to answer the question, how good is the learned policy? So we revisit the metric of imitation. So first, probabilistic imitation learning framework. Why we consider this framework? Because in this framework, we can do multiple demonstrations in terms of one task. By doing multiple demonstrations, more information can be conveyed from a human demonstrator to a robot. And so we can investigate data variability or uncertainty from the collected data set. But here's the problem for probabilistic imitation learning framework. That is the so-called competing constraints. Competing constraints emerge because of the existence of inconsistency between multiple imitated quantities. Consider example that we execute the joint trajectory mean from the multiple demonstrations. Then the resulting Cartesian trajectory is not necessarily matching the demonstrated Cartesian trajectory. And so here's the competing constraints problem. So in order to tackle this problem, we consider it from a multitask perspective. For multitask sequencing, we demonstrate each task for multiple times, and we have several tasks. Like task 1 denoted with this red curve, and this task, another task denoted with this blue curve. And in order to sequence them together, we can consider to use the so-called Gaussian product to blend the probabilistic trajectories in the Cartesian space. And to also preserve the imitation fidelity in the joint space, we consider to exploit the robot redundancy to optimize the null space parameters such that the robot can also imitate trajectories in the joint space level. So we can watch a video. The experimental setup is to make an iCub, which is a humanoid robot, for a cleaning and a pick and place task. And our goal is to sequence two tasks together with imitation of both joint and Cartesian space. For task 1, we do the demonstration. And then the robot can reproduce the taught task by itself. And then we demonstrate another task, which is a cleaning task. The robot can also produce it well. If we consider the imitation of Cartesian trajectories only, then the robot will fail to imitate joint space trajectories. So by exploiting its redundancy, the robot is able to imitate both Cartesian and joint space trajectories. But as you might have noticed, the robot cannot learn the orientation trajectories well, because the orientation trajectories are not considered. It motivates us to think of a new algorithm that can handle data with inherent constraints.
Anqing, can I have a question? Or I have to have all the questions afterwards?
Next part, when there are inherent constraints. So we consider to tackle this issue with a tool called structured prediction. So first,
okay. It's this one.
We introduce its definition. Structured prediction, first we review the concept for supervised learning. So in supervised learning, we try to find the functional relations between two sets, x and y, given a finite number of examples. Basically, structured prediction deals with the same problem, except that the output space can possess complex structured outputs, such as histograms, graphs, points on a manifold, etc. So to solve the structure prediction problem, a popular framework is called surrogate approach. So in this surrogate approach, we first do the encoding, where the encoding rule maps a quantity in the output space to a surrogate space, which is usually a vector space or Hilbert space. And then the learning is done in this surrogate space. So we try to find a mapping rule G such that it captures the mapping rule from the input space to the surrogate space. And then finally, we design a decoding rule, C inverse, which maps the quantity from surrogate space to the output space. So basically, because the original structure prediction from X to Y is hard to solve, so we solve this problem with the help of a surrogate space. To further simplify this surrogate approach, we introduce a concept called structure encoding loss function. So structure encoding loss function has this structure. It means that the loss between two quantities in the output space can be expressed as the inner product between the corresponding quantities in the surrogate space. With this definition, we can simplify the structured prediction further. So we will choose the multivariate regression in our surrogate learning, and the decoding rule is chosen in this equation. So for surrogate learning, we use multivariate regression or kernel ridge regression. So for the mapping rule G of X, we parameterize with W times phi of X, where W is the parameters to learn, and phi is a feature map. And by solving this optimization problem, we can have this G, this mapping rule G, denoted as G of hat. And we substitute this G of hat in this decoding rule. And by massaging these equations a little bit, we finally obtain this estimator, which solves the original structured prediction problem, as circled in this blue rectangle. To summarize, here lists the computation procedure for structured prediction. The first step is the training step, where we calculate the input-dependent weights alpha. And the second step is the prediction step, where we estimate the output S hat given an inquiry input. So we will solve this argmin problem. By solving this optimization, we are able to find the predicted value given an inquiry input X. So we will see how this structured prediction can facilitate the design of an imitation learning algorithm. Recall that we consider the problem under the framework of probabilistic imitation learning, which means that we have multiple demonstrations. Here, m equals 1 to m. It denotes the number of demonstrations, and n equals 1 to n is time step. By processing the raw data set, what we obtain is the probabilistic data set. It means that given an input x, the output is a probabilistic density function. It's a distribution, usually in the form of Gaussian. And there are multiple data processing techniques, such as Gaussian process or Gaussian mixture regression or neural network, etc. So our problem here is that given this probabilistic data set, we want to find a mapping rule S such that given an input X, the output is a probabilistic distribution P of Y. If the quantity Y in the original demonstration is a Euro-Euclidean point, then this distribution is just a multivariate Gaussian distribution. But if this quantity Y is some other form of data, like a point or manifold or quaternion or stiffness matrix, whatever, then the P of Y has a form of a Riemannian Gaussian. So the data structure is diverse here. In order to use the introduced structure predictor, we need to have a loss function between two probabilistic density functions. And by investigating the literature, we found out that the F divergence minimization is closely related to imitation learning. So for here, the loss function design for this delta, we consider to use tools from the F divergence. And F divergence is a class of divergence between probabilistic functions. The commonly seen KL divergence or Jensen-Shannon divergence belong to this category. So let's take the reverse KL divergence as an example. If we plug this divergence form into the estimator, then the loss function we get is this one. And it can be seen that the prediction for the mean value and the covariance can be separated. So we end up with two optimization problems. And by taking the gradient with respect to the mean or covariance, respectively, and setting it to 0, we can find the optimal prediction value. We can also try other forms of divergence. And in robotics, usually not only position is of interest, but also temporal trajectory, which means we also need the robot to imitate the quantities that has position and velocity. So it is possible to show that the proposed method can also deal with the temporal trajectory. Also for points on manifold, it is possible to show that the geodesic distance between two manifold points conforms to the definition for self-loss function. And in order to solve the optimization problem, we need to use the Riemannian gradient descent, which is a Euro gradient descent in the Riemannian space. Also, it is possible to modulate trajectory by weighting the corresponding points that we want to adapt through it. Results. Here, in the left figure, the dashed green line is the original demonstration trajectory. And we want the imitated trajectory to adapt through this red point. And our approach is depicted with this green curve. And the orange and blue curves are other imitation learning algorithms. can be seen that all the three algorithms can pass through this desired point, both position and velocity. Also, for imitation on remaining manifold, here is a sphere for an example. We have multiple demonstrations on sphere, and we can reproduce it with trajectory mean, and then we can adapt the starting point. So let's see the experimental results. Again, the experimental setup is to kinesthetic teach a robot arm. And in this case, it's a 2D planar example. And our goal is to reproduce the demonstrated trajectories as well as adaptation towards different waypoints. First, we do kinesthetic teaching for the robot to write on a board. And then we evaluate its reproduction capability. The robot is also robust to external disturbances. Then we make the robot to adapt for different waypoints, the starting point, waypoint, and end point. Next one is to kinesthetic teach a robot arm for polishing on a sphere. First is kinesthetic teaching. And then reproduce the learned skill. Also, robustness evaluation. And last, adaptation capability. The algorithm is able to adapt for multiple desired points. So let's consider another problem. Given different adapted behaviors, how should we benchmark different policies? Let's see this example. For 3 adaptation trajectories, the blue one has very large deviation from the original demonstration trajectory, but it seems that it can preserve shape well. But for the green one, the deviation from the original demonstration trajectory is small, but for the local area, there is very steep change for the trajectory. So how good is the learned policy? Let's see this toy example. If we, here again, the black curve is the demonstration trajectory, and the blue curve is the adapted one. Our intuition is that B, the mode B, preserves better imitation fidelity than mode A. But if we use the usual root mean square to evaluate their imitation fidelity, then we see that mode B has larger imitation error than mode A. So this motivates us to revisit the imitation metric to evaluate the imitation fidelity. Our idea is that the shape similarity should be reflected by the new imitation metric. And we can consider tools from statistical shape analysis, for example, Procrustes distance for trajectory similarity measure. So by using Procrustes metric, we see that the mode B has a smaller imitation error. Alternatively, we can also consider to adapt trajectories by non-rigid registration such as thin plate spline. So here, an illustrative figure. The green curve denotes the original demonstration trajectory. And what we want is to adapt several critical points for some other locations. So in this case, we want this red star point to go through this circled one. And by using thin plate spline, the modified trajectory can preserve the shape better. So to conclude, in this presentation, we addressed robot imitation learning mainly. And first, we see multitask sequencing in the probabilistic framework. But we noticed that sometimes we need to consider the robot orientation or some data that possess complex structure. So we move to structure prediction-based approach. Then we revisit imitation metric for measuring trajectory similarity. Thank you. If you have questions, please go ahead.
Can you hear?
There is already a question given up, but
Unfortunately, we cannot hear questions from the audience. Can you hear our questions?
yeah,
Do you have audio on the computer? Let's see. Maybe they can write the presentation with their question. I don't know why. Andrea, yes, I don't know why.
hello. We cannot hear you clearly.
Oh, okay. Can you hear? Can you hear me?
We are supposed to hear the sound from the audience, or
But anyway, I think we should pay more attention to the ones here. So anyway, anyone has any questions for Anqing? Any questions? There were, sorry, Anqing, there were 3 questions, very technical, I guess, from, if you go to the messages, go to chat. So there are 3 questions. He says, does imitation learning consider learning of states of desirable sequence or actions to achieve a goal or trajectories of pairs? Then there's another question regarding the surrogate function learn G, considering, or maybe you can answer the first question.
okay. Does imitation learning consider learning of states? I can answer the first question. Does imitation learning consider learning of states of desirable sequence or actions to achieve goal or trajectory of pairs? So in my work, I'm mainly, okay. So in my presentation, I only consider trajectories imitation. So the states action pairs are not considered. Surrogate learned if we do not have dogs for surrogate value. For the surrogate learning, but in the original surrogate approach framework, this encoding law C is designed manually. So one quantity in output space Y, one quantity in the surrogate space H. So there is one-to-one map. But if we consider this implicit encoding framework, say we assume the loss function has this form, then we do not need to consider about the surrogate learning explicitly, because it just disappeared because of this loss function structure, as well as this decoding law. Does this algorithm use temporal information from sequence somehow or considers points in learned trajectory to be subjectively learned as well as learning or distribution learning problem? Yes, for the temporal information, of course, for the data set, for each given input, the output is a position as well as a velocity. Y on the page 12, YP need to learn also the joint space. Y Cartesian space is not enough. Yes, but also if we go back to the motivation for the, it's also for the psychological reasons. If the robot can perform in a human-like manner or like a machine, then maybe we want it to behave more human-like. So by making the by imitating the trajectories in the joint space, the robot looks more like a human. But of course, in terms of task achievement, task space is enough. My question is X. What is X? What is G? What is Y? In examples or robotic tasks you provided, X, Y, G. Sorry, Andre, for the question regarding X, Y, and G, which page are you referring to? We don't see the presenter. Maybe someone put a phone looking to him. Also, the structured learning. What is the input? Jihong, for the structural learning, the input is xn. Usually it's time index, but also it can be also some other quantities such as position. And for the output y tilde, it's a probabilistic distribution, such as a Gaussian distribution. And for impedance control, the controller is not my contribution. I just use off-the-shelf controller by someone else.
That's the question.
Peng, what is the benefit of using the surrogate space? The benefits of introducing the surrogate space. The benefit of introducing the surrogate space is that we can transfer the original complex structure prediction problem to this surrogate learning. So imagine that a quantity from this output space Y could be very complex. And directly learning the mapping rule S is difficult or sometimes impossible. So we introduce this surrogate space H. And this surrogate space is usually a vector space. So now the learning problem is simplified as this input space X to this vector space. And for learning this mapping rule, we have multiple machine learning techniques. And as long as this mapping rule is learned, we just project this learned value back to this output space with this decoding law, C inverse. So first we assign each quantity in this output space Y with the corresponding value in this surrogate space. And we learn this mapping rule. And then given an input X, we will have a corresponding value in this surrogate space. And this value also has a corresponding value in this output space. So this problem is simplified.
Maybe we can bring the discussion to here.
Okay.
Anyone on the floor has any question? Anyone here has any questions?
The question online are not finished yet.
Oh yes.
Several.
No, but it will not finish. That's the problem. These guys, Jeffrey, Omar, Andre, Jico, they all work in imitation learning. From anyone here has any question from the research students? Something Kyle briefly attempted and dropped the idea of doing imitation learning. Anyone? Anything? Hello, I have a question about the first paper. What is the sequence of multi-task? Because I only see one task in the demonstration. What do you mean sequence?
You can think of it as blending. Blend trajectories together. So, for example, for task 1, we have multiple demonstrations, which is this red curve. And for another task, we do demonstrations for multiple times, which is depicted in this with this blue curve. So there are multiple tasks, and sometimes we want to blend all these trajectories together such that the robot behavior is more diverse or expressive or more complex. So we consider to blend them together with some activation functions given here. This is given manually, but of course there are some literatures dedicated to learning task priorities. But anyway, here it is given. And then by blending these trajectories together, you see we have a more complex Cartesian trajectories. So this is for the Cartesian part. And for the joint space part, we exploit robot redundancy for the imitation of joint space trajectories. That's the basic idea.
So it is trajectory to trajectory.
Yes. You see this one for this part is from here, and for this part is from red task.
And also for the structural prediction, what is the demonstration is a part of trajectory? It means so the demonstration includes many waypoints or just some start point or end point in the path.
The whole trajectory is the demonstration.
It means many points.
Yes.
It will connect the demonstration during the trajectory.
Sorry, what do you mean?
It means the input includes many points in the trajectory.
Input is time index. Output is like a Cartesian position, for example.
I have one question.
Yes, please.
So specific technical. This is well, you just joined. Very happy to have you in the group. So as you have seen, we have many projects, many things that we relate to manipulation. We're working with agents, we're doing sensing, some control problems. How do you think, or and you already actually involved helping us editing and working with some papers, so which I'm very grateful to you. Now, as in when we chatted months ago, we always try, this is the intention, to do very different type of work. Some new and sometimes weird sort of methods so that we can try to be the first doing it. So in the very nice work we have been doing with training experiments in universities, how exactly do you think you can help or get involved in some of these projects so that we may propose a firm first result in whatever aspect we can contribute to? You see in any of the projects that we are running, some area where
if you replace that black bar with a human head, then it could be a
black bar,
if you replace this black bar with a human face, then it could be a cosmic terminology.
you have kinesthetic
Yes.
come and move. Yeah.
Yes.
What if you only have, just as in the paper, you are helping to revise Jeffrey Noma? What if the observations you have is just spatial observations? For example, they have conducted God knows how many experiments with humans doing this procedure over a very weird, over human faces, some of it weird, yeah. But we have this spatial data, but it's not kinesthetic data. Can this information be used, for example, for...
From my understanding, you mean the input is some spatial data, right? From spatial to spatial.
But we only have, we can have tracker information tool. So you have a tool.
Yes, of course.
Right.
Of course. Yes. It can deal with a multi-dimension input. And I envision that if we also consider the input as some complex manifold data, then it could be interesting to investigate.
So we will learn. I mean, that's also that maybe in a more, I don't know if philosophical perspective. So when you learn from demonstrations, the learned skill cannot be better than the demonstrations, can it? I mean, you're learning. I don't know. You're learning to conduct. Let's say we stay in the phase procedure. We're learning to do this procedure, and we obtain all this data. You train the machine to do it, but this information, the machine cannot do it better than the human demonstrations. Is that correct?
I see. In demonstration, usually the demonstration behavior is assumed to be the optimal one.
Okay.
But we can consider how to. Yeah, it's open.
Yeah, there's I mean, I'm not doing this, but if we're able to model that, I mean, we take this because this is very much the case of the work Mudasir and Domingo are doing. We have these humans conducting the task, and so far, yeah, that's the best we can have. But through hard-coded methods, we have a machine optimizing, not optimizing, but improving in some way this performance. So if by taking the learning from demonstration paradigm, if we're able to model how exactly, I don't know, to put it simply as an initial stage, and then still be able to improve from there. So it's, I don't know if we can even make a catchy title like improving the master by human demonstrations, or how these titles in the learning community play with. Like using this paradigm of obtaining information from good, of course, human execution, but then having a method with the capability to improve that. How exactly? I don't know. I mean, basically, that is a different.
Yes. Yeah, I think it's. I mean, it is common. Like people usually use learning by demonstration to initialize robots policy, and for improving the robots policy further, reinforcement learning is really used to refine the policy.
And we reinforce. Another question: how about with, for example, the work this Kyle and Zoe are doing with manipulation of soft materials? Do you think something can be applied? Some of the methods you use to this application?
Yes. Before I considered an issue of manipulating a rigid object with a manual robot arm. I think if it can be interesting to make the object soft, like if I can manage to manipulate this object to track some given trajectories, and if we make this thing soft, then I can.
Sure. There are many. I mean, just what I want to mention. There are really many areas that you can work. I really hope you can get involved in these different directions we have. It doesn't even need to be a manipulator, I guess. What if we have formal agents? The demonstration is with hands. Say, for example, a cake or something. we operate. So you have a demonstration with these kind of things, but we reproduce it. Just conceive that we reproduce it with mobile agents, which they form different configurations. We learn this demonstration, but somehow transfer it to a different system, like mechanical system. Anyway, yeah, there are many
correspondence.
Right. So thank you everyone for coming. Thanks Anqing for joining. We spent quite some time today. Thanks to the audience here, to the still anyone still online? No, don't care. So anyway, thanks everyone. See you next time. Bye.